Our last speaker is Dr. Andrew Feitz, who will provide an update on our journey in assessing hydrogen and green steel potential. Andrew is the Director of the Low Carbon Geoscience and Advice section and leads the hydrogen module for the Exploring for the Future program. Andrew holds a Bachelor with Honours in Environmental Engineering from the University of Queensland and a PhD in Environmental Engineering from the University of New South Wales. Andrew joined Geoscience Australia in 2008 after a career as an academic researcher in water treatment technologies. His research interests include geological storage of CO2, the measurement of greenhouse gas leaks and seeps, geothermal and underground hydrogen storage.
Hi, my name is Andrew Feitz and I'm the Director for Low Carbon Geoscience and Advice at Geoscience Australia. It is my pleasure to share with you the hydrogen work that Geoscience is undertaking through the Exploring for the Future program. This work is supporting the establishment of the hydrogen industry in Australia. While it might not immediately spring to mind, Geoscience is playing an important planning role in the establishment of the hydrogen industry. Under EFTF, we have a number of areas of hydrogen research to support this planning. Geospatial economic analysis through our Hydrogen Economic Fairways tool, better mapping of underground salt resources and looking for new ones. Salt is key for large-scale underground hydrogen storage. We are also interested in natural or geologic hydrogen, a potentially cheaper source of hydrogen that could supplement manufactured hydrogen. This is a very new and interesting area of research, and little is known about the extent of this resource. I don't have a lot of results to share at this stage about natural hydrogen, but we have an extensive field program planned for 2022-2023. That's for next year's showcase. Finally, green steel. With lots of iron ore and good hydrogen potential, green steel is the next logical step. I will provide some initial analysis of this later in the talk. Firstly, why are we interested in hydrogen? Well, hydrogen provides a pathway for deep decarbonisation of the global economy. Electrification can get you so far, but for really tricky sectors, that's where hydrogen comes in. The first area of focus is the transportation sector, especially heavy vehicles such as trucks, trains and ships. Basically anything that uses diesel or fuel oil. Batteries are okay for short distances, but for long-haul transport, a tank of hydrogen is much lighter than a massive battery. Next on the list is blending hydrogen into the national gas distribution network, starting at 10% and then ultimately moving to 100% hydrogen. This has already started in Albury, New South Wales. At 10%, nothing needs to be changed. The steel piping, the appliances, nothing. 100% hydrogen gas network would also enable firming of the electricity grid by providing backup power, just like natural gas does today. Next is decarbonisation of heavy industry, replacing coal with hydrogen for the manufacture of steel, using renewable sourced hydrogen rather than natural gas for the production of ammonia and fertilisers, and many more. The Yarra Pilbara ammonia plant in this photo produces 5% of the world's ammonia. They are currently building a demo plant to replace hydrogen from natural gas with hydrogen from renewable energy. Many other plants around the world are doing this also. Finally, exports. With extensive natural resources, plenty of land for wind and solar, Australia is aiming to be a top 3 exporter of hydrogen to the Asia market and become a global superpower in clean energy exports. There are some pretty big projects planned for Australia, and I'll talk about these more later in the talk. The work presented today is part of Geoscience Australia's commitment to support the National Hydrogen Strategy. Consistent with the strategy, we consider hydrogen made from electrolysis from renewable energy and hydrogen made from fossil fuels with carbon capture and storage. Different approaches to hydrogen production require different natural resources, and our work helps identify the optimal location for hydrogen projects and hubs. At aush2.ga.gov.au, we provide a curated data set relevant for the hydrogen industry, but you can also access Geoscience Australia's vast data holdings and online tools. AusH2 is also home of HEFT, our Hydrogen Economic Fairways tool. At AusH2, you can click on any of the dots on the landing page and you will bring up details on individual hydrogen projects around Australia. A list of projects was originally developed by GA, but is now maintained and updated by High Resource. There are currently over 80 projects under development, construction and operating around Australia. All but 2 of these projects are green hydrogen projects, with some very big projects announced. For example, the Asian Energy Renewable Hub, located in the Pilbara region of Western Australia, is looking at installing 26 gigawatts of wind and solar power, covering an area of 6,500 square kilometres. This is about a third of Australia's current installed electricity capacity. Even larger projects are planned. The scale of hydrogen production in Australia is immense. Released in 2021, HEFT is built within the framework of Monash University's Blue Cap Code and provides a coupled geospatial economic analysis. This code was originally developed as a mineral prospectivity tool, but it was clear that the same approach could be applied to hydrogen developments, linking infrastructure with resources. It considers factors like the capital and operating costs of a hydrogen plant, distance to port and to water resources, and the renewable energy generation capacity at different locations and for different sized plants across Australia. The overall goal is to generate a map of net present value of hydrogen production at any location across Australia for a selected target hydrogen price. We released an updated version in 2022 that now includes a break-even analysis and underground hydrogen storage. Version 3 is not far away. And it will include export products such as ammonia and liquid hydrogen, and customizable operating and capital cost sliders for hydrogen production. This was based on feedback from industry. So keep your eyes peeled for news of an update over the coming months. We can add more data to the HEFT analysis to build up a rich picture for this new industry and where new infrastructure is required. The underlying map is a scenario from HEFT for a hybrid wind and solar production scenario and sending hydrogen to export. Red areas are profitable, blue areas are unprofitable, and white is the break-even analysis for this example. What's very encouraging is that the announced hydrogen projects are mostly appearing in our red areas, suggesting that our model is not too bad. Once you start adding electricity transmission lines and gas pipelines, you can start to see where there are infrastructure gaps. Also shown on this map are known thick salt locations around Australia in green, and the location of depleted gas fields. This brings us to the next topic of this talk, underground hydrogen storage. A major area of research under EFTF is underground hydrogen storage. We are looking at underground salt accumulations, which can be used to produce salt caverns, but also looking at the feasibility of using depleted gas fields for hydrogen storage. We are just wrapping up a major project with CO2 CRC and Schlumberger, looking at the geomechanical effects of hydrogen storage in a depleted gas field compared to other gases, making sure that the hydrogen storage is safe and doesn't cause fractures in the storage rock. However, salt storage is our main focus. You may ask, why are we focusing on underground hydrogen storage? Underground storage is much cheaper for large-scale storage of hydrogen than in other forms, such as liquid ammonia or liquid hydrogen. It is also much cheaper than hydrogen storage as metal hydrides or equivalent battery storage. Bloomberg New Energy Finance estimate that the world's first large-scale battery at Hornsdale in South Australia stores the equivalent to only 3.3 tonnes of hydrogen. Depleted gas fields, if found suitable, could store very large quantities of hydrogen to support seasonal demand. Salt cavern storage, based on most reports, is relatively cheap, primarily because it is more flexible, and the hydrogen can be cycled through it more times over a given period than depleted gas fields. Gas cleanup, if required, is also less likely to be an issue. So the search is on for salt. Australia has many sedimentary basins that contain salt, but thick salt accumulations, particularly halite, have been intersected by wells in only a few basins, namely the Canning, the Amadeus, the Adavale and the Polder basins. The photo is an example of the type of salt we're looking for. Found within the core archives of the Queensland Government's core store, it's a core sample of the Boree salt from the Adavale Basin, and in places is over half a kilometre thick. As you can see in the map, the Boree salt is the only known thick salt accumulation in eastern Australia, and is therefore a very strategic resource. Getting a better handle on the size and extent of this resource has been a priority for us. Mapping of the Ada Vale Basin hasn't really progressed much since 1980, and even that was largely based on 1967 analysis. In collaboration with Intrepid Geophysics and the Queensland Geological Survey, we have built a preliminary 3D model of the Ada Vale Basin, with a particular focus on the Boree Salt. We have mapped 3 salt bodies, and I would refer you to the extended abstract released as part of this showcase for more details. Given the lack of wells and good seismic in this area, there are still many unknowns, and there's a real need to acquire more data to better map this important salt resource. Another area of interest is the Polder Basin in South Australia. We have mapped the salt resource in the offshore Polder Basin and undertaken an initial design of a salt cavern. The offshore Polder Basin contains an excellent salt resource, approximately 1 kilometre thick of almost pure halite. The salt depth is good and is located only 60 kilometres offshore and within reasonable proximity to the Eyre Peninsula, which is scoped to be a major hydrogen hub. Offshore salt storage hasn't really been considered in Australia to date, but is under active consideration in Europe and the UK. This is potentially a very good option for this part of Australia. A single large salt cavern could provide the same amount of energy as Snowy Hydro 2.0. You don't need a lot of salt caverns to provide significant energy storage and help firm periods of low renewable energy output, as we have experienced in Australia recently. What about onshore? Well, the Polder Basin is a thin, skinny basin, and the same formation which contains the salt in the offshore extends to the onshore, admittedly with a whopping big geological fault in between. While there is good seismic coverage in the offshore, shown by all the lines in this figure, there is relatively little seismic coverage in the onshore. The number of onshore wells is also limited, and only one of these wells, Kilroo 1A, is deep enough to intersect the salt hosting Kilroo Formation, and it's located on the far eastern margin of the basin. So whether salt is present or not in the onshore Polder Basin is presently unknown. We are planning a gravity survey this financial year to see if we can provide evidence of salt and inspire further data collection in this potentially strategic area. Discovery of a thick salt accumulation in the onshore Polder Basin would be a massive boon for the hydrogen industry in South Australia. Now let's move to the Canning Basin in Western Australia. The Canning Basin is known to contain thick, extensive salt beds, but much of it is quite deep. A good option is to look for salt dipiers, where columns of salt have migrated towards the surface. We have used some of the fabulous airborne electromagnetic data, or AEM data, collected under EFTF and shown by Laura earlier in this session, to look for shallow salt leads. AEM can only resolve the top 500-600 metres, but this might be okay to look for disrupted zones above salt dipiers, as seen here at the Frome Rocks dipier, the only known salt dipier in this region. Working with the University of Queensland, we have identified some leads that are worth further investigation, and again I would refer you to the extended abstract for more details. The final basin we are looking at today is the Officer Basin. This large inland basin is known to contain salt, but wells to date have only intersected tens of metres of salt, not the hundreds of metres that are required. The seismic line collected by Geoscience Australia back in 2011 highlights the issue. We can see what seems to be large salt structures, highlighted in green, but all the wells to date have missed them. Salt hasn't really been considered a strategic resource in the past, and so it hasn't been a target of drilling. We have started the process of mapping salt leads in yellow in the Officer Basin and Arkaringa Basin based on the available seismic. There appear to be lots of salt structures, but they do need to be drilled to be proven up. This map also highlights large parts of the Officer Basin is without seismic or wells, and we have no idea whether salt accumulations are present there or not. As part of EFTF, we will be applying the AEM prospecting technique that we tested in the Canning Basin to the Officer Basin to identify potential new salt leads in areas without seismic coverage. The new AEM surveys, as you can see in this figure, are extensive and will cover most of the Officer Basin. You may ask why the interest in the Officer Basin. Isn't it a long way away? Well, not really. There is a very large 50 gigawatt renewable hydrogen project planned on the Nullarbor Plain on the very southernmost border of Western Australia and South Australia. At this location, the wind resource is good, the solar resource is not too bad, meaning you get a high hybrid wind and solar capacity factor. A salt discovery in the southern Officer Basin, clearly not one in a national park, could conceivably support storage needs for hydrogen projects along this part of Australia. With good hydrogen production potential, salt storage and iron ore resources, Australia has the ingredients for green steel. This map shows the best areas for solar, wind and hybrid wind and solar hydrogen production. Also shown are thick salt resources and iron ore reserves, both hematite and magnetite. The vast majority of our exported iron is as hematite, but studies suggest that magnetite may be more suited for domestic green iron making and steel making. This is because magnetite is magnetic and easier to separate and concentrate. The distinction between iron making and steel making is important. Iron making is the step before steel making, and it is a very energy intensive process with high carbon emissions. Many of the countries where we export our iron ore to have well-established steel-making industries, which they are unlikely to want to shut down. If we export green iron rather than green steel, this may prove a win-win for Australia and our trading partners. If we do go all the way to green steel, our preliminary studies suggest a good mix of wind and solar is ideal, with little difference for standalone production systems between WA's Pilbara and South Australia's Eyre Peninsula. However, if South Australia is able to supplement grid-based electricity and take advantage of low or even negative energy prices, this is projected to substantially reduce the cost of green steel production. Regardless, the cost of green steel is projected to fall as the cost of hydrogen and the cost of renewable energy decreases in the future. Carbon tariffs, such as the European Union's Carbon Border Adjustment Mechanism, will make green steel increasingly competitive in the future. Together with Monash University, we have produced a nice extended abstract on this work, which I would encourage you to read. Well, that's a brief summary of our work over the last 12 months. There are a few things I didn't get time to mention. This includes our geothermal hydrogen review with the University of Melbourne, a natural hydrogen from iron minerals review with the University of New South Wales, and salt dating work with Curtin University and the Geological Survey of Western Australia. Keep an eye out on the EFTF website for product releases associated with this work. There is an ambitious work program ahead, including further heft upgrades, building on the preliminary green steel work, further salt studies and release of an updated salt map, more geomechanical studies, and an ambitious geological hydrogen field campaign. I look forward to sharing these results with you next time. Finally, a big thank you to the 2021-2022 hydrogen team and our collaborators, and thank you for listening.